For a brief stretch of time on June 25, 1997, one of humanity's most ambitious achievements in space fell almost completely silent. Power failed across most of MIR station. Instruments went dark. The temperature began to drop. 3 people, 2 Russian cosmonauts and 1 American astronaut, floated inside a crippled, slowly tumbling space station, cut off from mission control, breathing recycled air in near total darkness, with little certainty about what would follow. One entire module of MIR had just been sealed off permanently. Inside it, personal belongings, scientific equipment, and sleeping quarters that would never be used again. Outside, a puncture in the hull, venting atmosphere into the void. The module, called Spektr, would remain sealed and depressurized for the rest of MIR's existence, a section of the station that could never be entered again. What unfolded on that June morning in 1997 stands as one of the most serious emergencies in the history of human spaceflight. MIR, the word means both peace and world in Russian, was launched on February 19, 1986 by the Soviet Union. It was the world's first continuously inhabited long-term space research station, a modular platform assembled in orbit over several years. It had been designed to operate for 5 years. By 1997, it had been in orbit for 11. The station was aging in ways that were becoming increasingly difficult to ignore. Crew logs and internal reports described equipment failures with growing frequency, cooling leaks, computer problems, issues with oxygen generation systems. MIR was a remarkable achievement of engineering, but it was also operating well beyond the limits it had originally been built for. It remained inhabited nonetheless. The reason was a cooperative initiative between NASA and Russia's space agency, Roscosmos, the Shuttle MIR program. Running from 1994 to 1998, the program was designed to prepare both agencies for the joint construction and operation of the International Space Station. It involved 9 space shuttle missions, docking with MIR and 7 American astronauts living aboard for extended stays. Michael Foale, a NASA astronaut with a PhD in astrophysics from Cambridge University, was the 6th of those 7. He had arrived on MIR aboard Space Shuttle Atlantis on May 15, 1997, joining Russian commander Vasily Tsiblyev and flight engineer Alexander Lazutkin. Michael Foale had been on board for roughly 6 weeks when the collision occurred, but the conditions leading up to it had been building for much longer. Just 4 months earlier, in February 1997, the same crew had dealt with a serious fire in MIR's Covant 1 module, caused by a faulty oxygen-generating canister. It burned for about 90 seconds, produced thick smoke, and forced the crew to wear gas masks. The incident drew scrutiny from both sides of the Atlantic about whether MIR was still a safe working environment. Despite that, the program continued. Then came the question of Progress M34. Progress cargo ships were the uncrewed supply vehicles that regularly docked with MIR, delivering food, oxygen, equipment, and fuel. They docked automatically using a radar-guided system called Kurs, and it worked reliably. But reliability had a price. Roscosmos, operating in the financially constrained environment of post-Soviet Russia, was looking for ways to reduce costs. The Kurs systems were manufactured in Ukraine, which had become an independent nation after the Soviet Union's collapse, meaning Roscosmos now paid foreign prices for them. So the agency began testing an alternative, a manual backup system called TORU, the teleoperated control system. With TORU, a cosmonaut inside the station would remotely pilot an approaching cargo ship using a joystick and a single video feed from a camera mounted on the spacecraft itself. The concept was straightforward. The execution, as it turned out, was not. Progress M34 had launched on April 6, 1997, and docked automatically 2 days later, delivering roughly 2,500 kilograms of supplies. Once those supplies were unloaded, the plan was to undock the ship and test whether Tsiblyev could redock it manually using TORU. The first attempt was made on June 4, 1997. It had to be aborted. Sibliev lost visual contact with the approaching spacecraft and couldn't safely complete the maneuver. It was a clear signal of how difficult this test actually was. The video feed was poor quality, and the single camera setup provided no depth perception. Judging speed and distance from inside the station on a low-resolution monitor was genuinely difficult. Despite this, a second attempt was scheduled for June 25th. On the morning of that day, the crew took their positions. Sibliev at the TORU controls. Lazutkin and Foale stationed at windows with laser rangefinders, attempting to manually gauge the distance of the approaching ship, because for this test, the digital radar telemetry had been turned off. The very data that would have told Sibliev how fast progress was moving and how far away it was simply wasn't there. What followed happened quickly. Progress M34 was not approaching at a manageable speed. Moving at an estimated 3 meters per second, well above the safe docking threshold of under 0.2 meters per second, the 7-ton cargo ship left almost no margin for correction. Sibliev struggled to see the vehicle against the bright reflective backdrop of Earth's cloud cover. At roughly 90 seconds before the projected docking point, Lazutkin looked through his window and saw it. The ship, massive, emerging from the glare of the sun, moving directly toward the station. Sibliev engaged the braking control, but it was too late. At 09:18 UTC on June 25, 1997, Progress M34 struck a solar array on the Spektr module, partially shearing it. A second impact followed, a direct blow to Spektr's hull. The crew felt the thud, and then they heard it, a hissing sound. The station was losing air. What happened in the minutes that followed has been described by those who lived through it as a controlled, focused struggle, driven not by panic, but by trained instinct and, in at least one case, sheer physical determination. Alexander Lazutkin moved immediately toward the Spektr hatch. Running through it were numerous power and data cables connecting Spektr's solar panels to the rest of the station's electrical systems. Those cables had to be disconnected before the hatch could be sealed. There was no time for a methodical approach. He worked through them one by one, cutting and disconnecting as quickly as he could, while the station's air continued to escape through the puncture in Spektr's hull. He later described those minutes with characteristic directness. I was doing one thing, disconnecting cables. I had no other thoughts. Meanwhile, Michael Foale moved toward the Soyuz capsule, the station's lifeboat, and began preparing it for potential evacuation. But what he observed was that his crewmates were not retreating. They were fighting to save the station, so he stayed and helped. The hatch was sealed. The depressurization stopped. From the moment of impact to the sealing of the hatch, roughly 10 to 14 minutes had passed. The crew was safe, but the station was in serious trouble. With Spektr isolated, MIR had lost access to a significant portion of its electrical power. Spektr's solar panels had generated roughly half of the station's total electricity, and now, either damaged or disconnected, that power was gone. Estimates placed the immediate loss somewhere between 30 and 50% of MIR's total generating capacity. Systems began shutting down, batteries drained. As Foale later described it, within 20 to 30 minutes after the collision, every single piece of equipment on the station went dead. It was a completely silent station. It's quite eerie to be in a station in space where there is no sound except for your own breathing. And then it started to get cold. Really, really cold. There was one additional problem. The force of the collision had knocked MIR off its orientation, its attitude, in aerospace terminology. The station had begun a slow, uncontrolled tumble. The remaining solar panels were no longer aligned with the sun, and without sunlight, they couldn't generate power. Without power, the station couldn't fire its thrusters to correct the tumble. The situation was compounding on itself. Communication with Mission Control in Moscow had also been disrupted. This is where Foale's background became unexpectedly critical. With the station's computers offline and no reliable telemetry reaching the ground, someone needed to determine how fast MIR was rotating and in what direction, so that controllers could calculate a precise thruster burn to stabilize it. Foale used a method that required nothing more than a window and an understanding of physics. By holding his thumb against the stars and tracking their apparent movement, he estimated the station's rotation rate and orientation. Controllers on the ground used those calculations to fire the Soyuz thrusters, docked to the station at the time, with enough precision to bring the tumble under control and gradually reorient the solar panels toward the sun. Power began to return. It was an improvised solution to a problem that no procedure manual had anticipated. Foale later reflected that the recovery was a great testament to the crew's resourcefulness. Tsibliev, however, bore a significant personal toll. In the weeks following the collision, ground doctors monitoring his health detected a cardiac arrhythmia, severe enough that an early evacuation was considered. He remained aboard and completed his mission on schedule, but the strain of the incident and the controversy that followed weighed heavily on him. In the immediate aftermath, Russian officials and engineers at the Energia Corporation pointed to Commander Tsibliev, characterizing the collision as the result of pilot error. Tsibliev pushed back directly. He stated publicly that he had not been provided adequate radar data during the approach, that his preparation time on the TORU simulator had been insufficient, and that ground management had applied pressure to conduct the test on schedule, despite known difficulties. "It has been a long tradition here in Russia," he said, "to look for scapegoats." The NASA-led Stafford Review, a safety task force convened by NASA Administrator Daniel Golden and chaired by General Thomas Stafford, reached a different conclusion. The investigation identified a chain of contributing factors. The Progress ship had been improperly loaded, shifting its center of mass. Critical radar telemetry had been absent during the approach. The video feed provided no depth perception, and Tsibliev had not had adequate simulated time to prepare for the specific conditions of the test. Stafford's team concluded the test was not well coordinated and stated clearly that no similar experiment would be conducted without full joint approval going forward. Energia eventually acknowledged these operational shortcomings. In the United States, the collision, coming just 4 months after the MIR fire, intensified an already active debate in Congress and the press about whether NASA should continue sending astronauts to the station. Critics described MIR as an aging platform operating far beyond its design life and questioned whether the scientific value of the shuttle MIR program justified the risks being taken. NASA Administrator Golden responded by affirming that all decisions would be based on technical and scientific assessment, and that the program's value, particularly as preparation for the International Space Station, remained real. The program continued. In September 1997, astronaut David Wolf arrived aboard MIR on STS-86, replacing Foale, who returned to Earth after 123 days on the station. Repairs to MIR's power systems progressed through the summer and fall of 1997. In August, Commander Anatoly Soloviev, flight engineer Pavel Vinogradov, and Foale conducted an internal spacewalk inside the depressurized Spektr module. They installed a specially fabricated hatch cover fitted with pass-through ports and ran 11 power cables from Spektr's still functional solar panels back into the station's power grid. The work took approximately 5 hours. When it was done, Foale reported that things have really started to come back together. Conditions are like before the collision. Subsequent internal spacewalks in October restored approximately 70% of Spektr's pre-collision power generation capability. Spektr itself was never repressurized. It remained sealed for the remainder of MIR's operational life, a permanent record of what had happened that June morning. MIR continued to operate until 1999, when it was left uncrewed. On March 23, 2001, the station was intentionally deorbited, breaking apart and burning up over the Pacific Ocean, 15 years after its launch. 3 times the lifespan it had originally been designed for. The lessons drawn from the 1997 collision became part of the foundation on which the International Space Station was built and operated. Stafford's review established that close proximity operations between spacecraft would require full coordination between all partner agencies. Automated docking systems were prioritized. Crew training protocols were reassessed. The value of redundancy in power systems, in life support, in decision-making was made tangible by what MIR's crew had endured. And, perhaps most notably, the TORU manual docking system, the very system at the center of this incident, was not retired. Modernized versions of it remain in active use today on the International Space Station, serving as a backup in the event automated systems fail. The technology was not abandoned. It was improved. That, in many ways, reflects the enduring character of human spaceflight, not the absence of failure, but the sustained effort to understand it.